Hey you guys, Lisandro here, and today I want to make a special blog. So lately I've been, for curiosity, I've been checking out Green Beetle's channel. And Green Beetle's channel is mainly about forging metal. But mainly he specializes in forging like almost any type metal object or metal structure into actual knives, and I really like his channel. Really fine craftsmanship. It's not that many people that have the craftsmanship to just get any metal that you can think of. Well, not necessarily any metal, but any iron object, and just craft it into an actual knife. So I'm gonna leave a link in the description to his channel, so go ahead and check it out. But what I want to focus on is something related to this channel, and that's the whole deal with forging steel. Now, steel is a very versatile type of metal. It allows us to create a variety of different structures, tools, and things that we normally would not be able to with just regular raw iron. Now, what exactly is steel? Steel, by definition, is defined as a hard, strong gray or bluish gray alloy of iron with carbon and usually other elements, used extensively as a structural and fabricating material. So basically, steel is defined as an alloy. However, I consider that a misnomer, and here's why. If we look at the definition of what an alloy is defined as a metal made by combining two or more metallic elements, especially to give greater strength or resistance to corrosion. The second definition is defined as mixing parentheses metals to make an alloy. Now I want you all to focus on this. A metal made by combining two or more metallic elements. And I emphasize greatly on metal and metallic elements. And if you look at the second definition as well, I also emphasize on the word metals in the second definition. Being that said, let's go back to the definition of steel. Now notice this part of the definition. It says of iron and carbon, which are the two primary elements used in most of the steel used today, apart from other elements that they may use for things like such as wear resistant, corrosion resistance, or depending on any other application they may use steel in, which is why it says and usually other elements. But primarily steel is composed primarily out of iron and carbon, which gets me to my next point. Can steel be classified as an alloy? So let's break it down a little bit. In order for you to have an alloy, you have to have a mixture of two or more metals. We know that iron is a metal. However, carbon is not. And here's the description of carbon. Carbon, parentheses from Latin carbon, quotation mark coal, and this is pretty much the origin of the word carbon, which is the Spanish word for coal or charcoal. It's a chemical element with the symbol C and atomic number 6. It is non-metallic and tetravalent, making 4 electrons available to form covalent chemical bonds. Okay, and what it's referring to there is when you get into like organic chemistry, they're gonna cover things like octet rules, pi bonds, sigma bonds, and so on. Things like that. That's what it's referring to. But what I want to focus on here is the word non-metallic, which pretty much is saying that this element is not metallic at all, therefore it cannot be classified as a metal. Being that said, we can deduce that the majority of steel used is mostly comprised of metal or metals and non-metal. Being that the case, steel cannot be classified as an alloy. So if that is the case, then what classification does steel fall under? And the answer is quite simple. If we look at the description of ceramic, it states, a ceramic is an inorganic, non-metallic, solid material comprising metal, non-metals, or metalloid atoms, primarily held in ionic and covalent bonds. We know that iron is a metal and that carbon is a non-metal. We also know that carbon is able to form covalent bonds because of its tetravalent structure. And we definitely know that iron is able to form ionic bonds, which is stronger than any other type of bond. So in reality, steel approaches more the description of a ceramic, and we can say that steel falls in the category of a ceramic and not an alloy, which pretty much makes a lot of sense. Now, originally I wanted to use a chart similar to the one Green Beetle uses to display the percentage of carbon and the different type of carbon-iron combinations, like medium steel, cast iron, and so on. However, I did find something not exactly similar, but that displays the different percentages of carbon within steel. As you can see here, you have different types of iron and steel, and you have the different percentages of carbon for each of them. You have pig iron, white cast iron, gray cast iron, malleable cast iron, tool steel, high carbon steel, medium carbon steel, cast steel, and low carbon steel. Okay, so if you look at the top one, it says pig iron and it says 4%. Now the thing about pig iron is that pig iron is very brittle. If you have gotten like old sewer pipes or old tubs, those old iron tubs from back in the 1950s or 60s or around here, those are mainly cast iron or pig iron, and the thing is that those break, and there's in a lot of old objects there's a lot of pig iron or cast iron and so on. The thing about that is that if you notice the percentage, it says 4% carbon, and it's the reason why it's brittle is because of that percentage of carbon. Now, if you look further down the list, it says white cast iron, gray cast iron, and malleable cast iron. And the thing is that the lower grade of carbon that it has, the more malleable it is. Now let's go in the other direction. Now what would happen if instead of adding 4% carbon to iron like you do with pig iron, you added 25% carbon, or even as much as 50% carbon, 50% iron, or even higher content of carbon? What you would get is what they call iron carbides or ferro carbides, which are classified as ceramics. Even though steel, which is also a iron carbon compound, is not referred to as a ceramic, despite it falls into the description of what a ceramic is. Now these are very similar to ferrites, and these ferrites, they also consider them actual ceramics. Now, before I go any further, there are some things that I want to clarify. A lot of people, when they hear the word ceramic, they automatically assume things like porcelain, ceramic floor tiles, dishes, pottery, and the list goes on. While they are not wrong in their simplistic concepts over what a ceramic is, they do not grasp the overall definition of what it is, the entirety of the vast quantity of its applications, such as use in grinder disc, telecommunication, automotive industry, glue compounds, thermal insulators for electronic components, furnaces, rocket components, dentistry, material science, superconductors, and so on, or the variety of different types of ceramics, such as ferrites, iron ferrocarbides, silicon nitrides, or silicon carbides. It's like salt. When people hear of salt, they think of plain old sodium chloride table salt. They don't think of other salts such as magnesium chloride, potassium chloride, etc. So now that I got that out of the way, getting back to the main point, like I said, ferrites and iron ferrocarbides are similar. And the way they are similar is not only because they are ceramics, but also because of their brittleness. That depends, of course, on the type of iron ferrocarbide. But despite these similarities, both ferrites and iron ferrocarbides are in reality greatly different. Ferrites mostly consist of iron oxides, not to mention that only a very small amount of carbon can be dissolved in ferrite at a maximum solubility of 0.02 weight percent at a temperature of 723 degrees Celsius, which is actually 1333 degrees Fahrenheit, and 0.001% carbon at 0 degrees Celsius, which is actually 32 degrees Fahrenheit, which I would say is very little amount of carbon. It does not even reach the amount of carbon that low carbon steel has, as opposed to iron ferrocarbides such as cementite, which has a percentage of carbon up to 6.67%, which is more carbon than that of pig iron. Cementite is a hard, brittle material. It's like I was saying earlier, the higher the carbon percentage, the more brittle it is. So why is that? And the reason is very simple. Metals are known for various properties: their conductivity of both heat and electricity, strength, heat resistance, wear resistance, corrosion resistance, but most of all, its malleability, the ability to bend and shape it to any desired shape. But the thing with these iron carbon compounds, or better yet said, metal non-metal compounds, is that the higher the percentage of non-metal in the compound, the more it loses its malleability, the more it loses its metal-like properties, and adopts more of the properties approaching a ceramic. It takes on a characteristics in which malleability becomes proportional to the hardness and brittleness of the material. Of course, various factors have to be considered, such as temperature, pressure, the type of element within the compound, and certain properties the compound might have gained due to the type of elements in the compound, as well as many other factors. Now, before I conclude this video, I just want to add to this. The reason why steel is considered an alloy is because even though it's a compound with a non-metal, it's a compound that retains a good portion of its properties as a metal due to its composition, which constitutes more metal than non-metal. Hence, they call it an alloy, despite its properties approaching more to the definition of what a ceramic is. If you're interested to know more about iron carbides, check out nature.com's page in regard to iron carbides. Morse Bauer's spectroscopy of iron carbides, from prediction to experimental confirmation. I'll have a link in the description down below. Anyway guys, thank you guys for watching. I hope you enjoyed this video. Please like and subscribe, and also pledge to my Patreon. And I'll catch you guys next time. Bye.